My name is Niels. I'm a PhD student at the Delft Technical University in the Netherlands. I'm from the Parallel Distributed Systems group, so I'm a peer-to-peer guy, so maybe I'm going to be a bit too quick with the peer-to-peer stuff, so feel free to stop me at any point. Okay, so I'm here presenting my paper called ReClaim, which is yet another decentralized online social network. So we've all known social networks. They're hugely popular. Facebook has more than 1 billion monthly users. Google allegedly has 500 million. But these social networks have centralized storage. So the centralized storage has some questionable security. There's a big corporate entity which stores all our private social data, and they actually have an incentive to make money from it, because they sell that private information to ad companies and the like. There have been a couple developments in trying to use the existing social networks to exchange encrypted content, but we feel that there's an incentive for the existing social networks to prevent users from encrypting their content, because that's how they make money. So if everybody starts encrypting client-side, they can't make money anymore. So we feel that decentralization is the way to go. It improves security by removing this centralized point of storage, thereby also removing or lowering the running cost, because you don't have a lot of servers to maintain. But decentralization still potentially exposes the social graph and makes clients maybe more vulnerable than having a big secured server. So with ReClaim, we want to design, implement, and evaluate a decentralized online social network, which again doesn't have a central server. We want to reduce the exposure of the social graph. It's very difficult to prove that you're not going to expose it, so let's keep it at reducing it. We want to replicate and store updates at friends. So updates in our system are all messages transferred between friends. So wall posts, likes, images, etc. And we want to replicate these messages at your friends. So let's assume me and her are friends. My messages are going to be stored at my personal peer, but also at her to replicate it at my friend, and vice versa. And we want to deal with NATfirewalls, intermittent network connectivity, all the stuff you have to deal with in a peer-to-peer network. So for security, we chose not to use broadcast or attribute-based encryption. I don't know if everybody's clear with those concepts. I'll explain them in a short way. So broadcast encryption is basically you encrypt some binary stuff once with some, let's say, AES, and then you encrypt this AES key with the different public keys for all the destinations. So basically you have a single encrypted file with the keys, the decryption key encrypted with the public keys of the destinations or the target audience. Attribute-based encryption is a bit more complicated. It basically allows you to target a group of users, users having a particular attribute. But it's really complex to do in a decentralized setting. You usually need to have some kind of certificate authority or some centralized component again, which we want to avoid. So we just use separate encrypted messages for each friend, basically. So even if you're targeting a wall post or an update to multiple friends, we just create separate encrypted messages. So these two techniques are really nice. They would reduce the bandwidth consumption, but increase complexity. So that's why we chose not to implement those. So in ReClaim, peers with overlap, so peers with sharing friends, they can actually construct a partial social graph because they know from each other that they're sharing friends. Peers without any overlap, they cannot. We're going to use, I'll introduce it in a bit. We're using private setting intersection, which allows us to do this, or guarantee this even. Peers with overlap, so peers which have shared friends, they store and exchange messages destined for each other. So that's the security part. So all the updates, all the messages are encrypted using the public key of the destination. So for each friend, we create a separately encrypted message. They only contain the destination in plain text. Everything else is encrypted. They're stored at the friends of the destination and the destination itself, so the targeted friend. And we synchronize those messages using a Bloom filter. Bloom filter are compact hash-like representations, which allow you to synchronize quite efficiently. So we determine which friends are shared between two random pairs using an existing approach to the private set intersection problem. This is an approach from Friedman et al. And it uses the Payet homomorphic encryption scheme. So homomorphic encryption is probably also not really known. So basically, homomorphic encryption allows you to, after encrypting a particular value, so let's say 5 or I don't know, still do multiplications and additions. So you have an encrypted value, which is now this crazily big, long, and you can just do times 3. And then after decryption, you actually multiplied the normal value, let's say. Friendship are exchanged or established by exchanging the public keys. So a lot of related work actually uses a DHT. So a DHT is a distributed hash table, and we don't. So why don't we use a DHT? So in peer-to-peer, DHTs are commonly used to store any data at a particular key. You usually compute the key using a hash function. And to look it up, to look up a value, you compute the key, and you look in your routing table to actually be forwarded to the particular peer storing this value. But in a social network, if you use a DHT, you're actually telling people who your friends are. So thereby basically exposing your social graph. Typically, in a DHT, you have these ever-increasing distance links, active links in your DHT. So if I wanted to send a message to this guy, I won't have a connection to all pairs in the network because it's millions of guys. You'll probably have increasingly logarithmically increasing distance links in the DHT. So you can visualize this ring as numbers. So let's say this is identifier number 0, and then clockwise you get increasingly higher identifiers. So I'll probably only have the furthest away link I maintain is this guy here. And because this is the furthest away link, he can probably just he knows that I'm gonna look up a particular value and can actually see that the request came from me, exposing the social graph. But if you don't have a DHT, we needed to have an alternate method to detect which friends basically are shared between two peers. So thereby, again, we're using this private set intersection. Okay, so this is the slightly complex version. I got an example in the next slide. So basically what we do, we build a polynomial. And first, we convert the items in your friend set, so your friends, the public keys, we convert them to numbers. And then we construct a polynomial which has roots in those numbers. Basically, if I'll just show the example. So let's say Alice has 2 friends. She converts these 2 friends into a number, which you can just simply do with hashing. It's a big number, but it's still a number, right? And she also puts her own public key in this friend set. So you have 3 items in total. So let's say I got this 0.5, 1, and 4. Those are my 4 hashed public keys converted into a long or into a float. And I construct a polynomial from these 3 numbers. You get a polynomial which is more or less like this. And it's, That's the representation. So in the Friedman algorithm, you basically encrypt these coefficients, this 1, 5, and 6.5. You encrypt them using the Pouwelse scheme, and you send them over the line. And then Bob, which is on the other side, evaluates the polynomial for his inputs, his friends converted with the hash function into numbers. And then basically, this is his evaluation. So he puts in 3 in this example. The result is -5. This is still encrypted, so Bob doesn't know this value. Bob multiplies it with a random number, adds the original input, and if it doesn't overlap, because 3 wasn't in Alice's initial input set, it results in a random number. But if Bob has a friend which does overlap, so for instance this one guy, the evaluated polynomial will be 0, because I made sure with the polynomial that it has roots in my friend. So this is still encrypted, but with the Pouwelse scheme I can multiply it with a random number, which still is going to be 0. I'll add the original input, which is 1, so the result is an encrypted 1. So if Bob then sends it back, you basically, Alice can decrypt this encrypted 1 value, and basically knows that it's in her input set and knows that this friend is shared between her and the random pair on the other side. Yeah, this all works quite nice, but we wanted to improve the speed at which friends are found. So Bob in our system forwards the friend request, so this FSF request, to some other pairs. This basically allows us to speed up the process of finding similar pairs. So allows us to speed up the process of finding your friends basically in the system. So this is a small representation of that. So you have the initial friend request, which is this handshake from Alice. Bob forwards the handshake to Charlie and a couple others, waits for their reply, and then replies with a bundled reply, which allows Alice to basically determine the shared friends between her and Bob and Charlie and his neighbors. We're using Bob as a proxy in here because of NAT. We can't simply connect to Charlie because there's probably a NATfirewall in between. And Bob already had this active connection, so he can just forward the request. So because we use this private set intersection, we have a couple guarantees. So basically, because Alice is using this private set intersection stuff, Bob cannot know if the output is 0 or a random value. So if he would be able to fake a 0 value, he would be able to fake shared friends, which he's not. And he can also not decrypt the responses of the others after he forwarded it to Charlie and etc. And Bob is actually protected as well because we multiplied the result of the polynomial by a random value. So Alice can't really detect what Bob's input was if it wasn't a shared value. So we built this system on top of Dispersy, which is our peer-to-peer platform, let's say, data platform. And Dispersy replicates data items, which are just blobs. These data items are stored in a local database, and you can define types of overlays or types of networks, which determine the content or the body of a message. Peers can join one or more overlays. So in this case, our ReClaim is an overlay. So you can join more than one ReClaim overlay. You can instantiate your own ReClaim overlay, etc. And then in each overlay, peers synchronize their data using these Bloom filters. And basically, using the Bloom filter, we advertise which messages we have, and then the missing ones are replied. So this is a small overview. So Dispersy already provides it with this peer selection. So it has a more or less a semi-random peer selection scheme. So after selecting a peer, we initiate this friend shared friend handshake, which is this private set intersection stuff. So after doing this, we actually know which friends are shared between me and the guy on the other side. So then we look into our local item storage, fetch the messages which are basically destined for me and the friends or the shared friends. We create a Bloom filter, we send it to the guy, and he replies with all the missing messages he has from the received from our shared friends. Basically, if you receive any of these updates, we give her the final destination because we have the destination in plain text, and then we decrypt it if possible. So we made a small proof of concept. It's based on the core of Tribler, which is yet another piece of software of our group. It's a small GUI. So this indicates if a peer is online, or at least if you have an indirect connection to one of these shared friends. We implemented some chat messages, that sort of stuff. And we use the peer cache to improve the speed of bootstrapping. So basically, after you discover the friend, you'll store the IP address in a small database and use it the next time. So using this proof of concept, we emulated the performance of this system on our supercomputer. So this is, we used 20 nodes. We used a small Facebook data set, which is 4,000 peers. So basically, a peer really doesn't know if it has a direct or an indirect connection to a friend. It just knows if it's shared. It doesn't really care, actually. So we plotted direct connections and indirect connections. So if you have some path to a friend or a direct connection. And then without cache and with cache basically determines if we use the peer cache. So if we use this small cache file of peers we connected to in the previous run. Basically, the cache consists of 36% of your friends, because we know from measurements that 64% of peers use a NOT, so we use 36% of friends. So initially you get quite a nice gain from this peer cache, because obviously you connect instantly to these 36%, but then the discovery process flattens out a bit. It takes quite a while. So it takes like 30 minutes to reach 75%. Indirect connections are much quicker, which makes sense because you need less connections. We looked a bit into this, why this is basically flattening out. We expect it's clustering, which is more or less what you would like to see in a social network, because peers in the social network are clustered. But we're guessing it's clustering a bit too much, so it doesn't do enough exploration. And that's why it's not stuck in local optima, because it's still finding some peers, but we need to add some more randomness in there. But it was a bit out of scope for the stuff, for this paper. So summarizing, we've shown that it is possible to build this decentralized social network. We've implemented this friend-shared friend handshake, which computes the overlap between two peers without disclosing the peers which don't overlap. We use dispersity to efficiently synchronize the updates. And we've shown in this small evaluation that you can actually find 95 or have an indirect connection to 95% of your friends within 10 minutes. That's it. Question?
Functionality model are you searching for? For example, I think use of one of the common functions that, say, Facebook and those kinds of social network platforms provide is to suggest friends, to suggest people who you may know. Well, look, here's this person you're not currently friends with, but your friends list overlaps heavily with theirs. Maybe you know them. You want, and it sounds like, this will very purposely intersect them out and make them invisible. But maybe sometimes you want, the users want them to be visible. How do you envision? Have you thought about that? And how do you envision trying to address that? Functionality, privacy.
Yeah. So initially it's going to be a problem, right? Because if you really consider the cold start problem, so you have no friends at all, you just join this ReClaim system, then it's going to be a problem. If you're bootstrapped a bit, so let's say you have 10 friends already in the system, you could employ other types of algorithms, right? You could employ, instead of private set intersection, you could compute the union or compute some most overlapping friends and use them still as a recommendation. In this system, so we don't really, our main focus of this private set intersection was to not expose anything to people which don't have any overlap. So I think it's still just to, after you've determined that a guy is actually your friend or has some overlap with your friend, that you can use or expose a bit more information then. Because those are not maybe the bad guys, it's really the rest of the world you don't want to communicate with.
Okay, so you might use the existence of some overlap as kind of a authorization to reveal potentially more overlap.
Yeah, in the end, it's conversion to something which is almost recommendation, right? Because you just connect to a couple guys, which is more or less top K recommendation. Yeah.
So I have a couple of comments about the design decisions that you made. First comment is about the encryption scheme that you used. So you mentioned that you didn't use attribute-based encryption because it requires central service. I'm not quite sure if that's really true. I think distributed social networks can also use attribute-based encryption. So if I'm the owner of some data collection, I can assign attributes to my friends, share some keys with them, and then...
The problem, I feel it's revoking. Revoking is really a big problem in this attribute signed encryption scheme. Because, okay, let's say you want to revoke a particular attribute from a peer. How are you going to convince everybody that this guy doesn't have the attribute anymore? Or I think the revoking part is the difficult part. I agree with you that just granting someone the permission is quite, that should be okay. But revoking should be quite problematic.
I'm not sure if your design handles revocation at all.
No. So the revoking, okay. Revoking, okay, so let's assume that if you're going to send an update to someone, right, and at that point in time he had the permission, then it's out, right? So then revoking is more or less the same. At some point in time you're going to say, okay, this guy isn't going to get updates anymore, and that's the same in our system as in the others.
Maybe we can take this offline. I have a second comment, which is about the design choice of not using a DHC. One of the reasons you mentioned was that it exposes the social graph. So I feel like given the bandwidth overhead and the time overhead that it takes to discover your friends or friends of friends, I think it might also be an alternate possibility to do an anonymous lookup in a DHC. I wonder what the trade-offs would be.
You could, there's this bootstrapping problem that's basically a different thing, right? So I have, okay, so this securing the DHT is one of the problems I had with, which I pointed out. Another one is like more, I don't know. Personally, I would like to see my data stored at my friends. I would prefer that over having it stored at some random guy at some random location. Because in a DHT, if you start storing stuff in a DHT, you have no control whatsoever where it's going to be stored.
For the data is encrypted, why does it matter where it's stored?
That's true. Yeah, sure.
Isn't that the argument that the original Bitcoin design was perfectly anonymous because nobody had to reveal who owned each key?
No, I think the design choice I suggested it's something stronger. You actually use some. Think about using Thor or using Thor to do a lookup. This is a very naive example.
Yeah, but then you're gonna go into something which is DHT, but it has like proxies in between. So you're not gonna use the DHT as is, but you're gonna proxy it a couple hops and then use the DHT. Okay, then already, yeah, but there's quite some overhead there as well. Huh? So I don't know what is better. I agree that this 10-minute thing we're using now is a bit slow. But you could do other things. So we're actually doing this handshake once every 5 seconds. If you want to have like a more aggressive bootstrap, you could lower that in the initial 5 minutes, let's say. And there's stuff you want to do. You can actually do in this system to make it more performant, but we didn't because it was a bit out of the scope.
Any other questions? Yeah.
This is actually one suggestion I was wondering if you first explore. So to establish a new social network, this sounds like impossible work, but you can actually establish encrypted, secure social network on top of existing one,
Yeah.
especially for those social network that is, let's say, based on the XMPP.
Yeah.
And I think that might be practical and actually be useful for people that do really care about the security to keep their social network, and especially the information.
Oh yeah, that's true. So the XMPP, that would be a nice example. But then again, like I said in the introduction, I think like Facebook and all the big guys, they're going to actively block encrypted content because they have to have access to your private data in order to make money. So, and that's their goal, right? They want to make money from their users. So if you start a free ride on top of an existing, let's say, big money-driven social network, you're going to run into problems being blocked altogether or have to do all kinds of crazy